Hey y'all, welcome back. This is going to be our 14th lecture, and we're going to cover sections 4.2 through 4.6 on exponential and logarithmic functions. We're going to jump right into some definitions. So if b is a constant real number such that b is greater than 0 but not equal to 0, then for any real number x, a function in the form of b to the x is called an exponential function of base b. That should be b to the x. So some examples of exponential functions are going to be stuff like 2 to the x, 3 to the x. You could even have 1/2 to the x, 6 to the x, anything like that. Versus not exponential functions are essentially anything else that we have. So we had x squared, you can have 1 over x, x to the fourth, anything like that. So exponential is when you have an x in the exponent. All right. So for some examples, we want to draw some graphs of the following functions. What we're going to do first is make a little table for x and y. So this is going to be for number 1. And then I'm going to pick some of my favorite points, -2, -1, 0, 1, and 2. And then we plug them into the x spot. So here, when x is -2, that means we're going to have 2 to the -2, which is the same thing as 1 over 2 to the 2, which is 1/4. So -2, 1/4. And then 2 to the -1 is just going to be 1 over 2. So this is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. All right. So for number 1, I'll plot some points for us. So let's see. We'll go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And we'll have 0, 1. We have 1, 2. 2, 4, and then on the left side we have -1, 1/2, -2, 1/4. So it is going to look something like this. With exponential functions, it does have asymptotic behavior at y equals 0, because you can never raise a number to a power to get 0. Like 2 to any number will never be 0. So for number 2, we'll make another table. And then again, my 5 favorite numbers. All right, so we have 1/2 to the -2 is going to be the same thing as 2 to the 2, which is 4. 1/2 to the -1 is just going to be the same thing as 2. 1/2 to the 0 is 1, since any number to the 0 is 1. 1/2 to the 1 is 1/2. And then 1/2 squared is the same thing as, 1 squared over 2 squared, which is 1 over 4. So then for my graph of 1/2 to the x, I'll have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. All right, so we always have 0, 1. Then we have -1, 2, and we have -2, 4. And on the right side, we'll have 1, 1/2, and 2, 1/4. So if you notice, what's interesting is these are almost flipped over the y-axis. So you can see this one goes up really fast on the right side, and this one goes up really fast on the left side. And that's how you graph exponential functions. All right, let's move on. All right, now we want to graph this, and we want to use transformations because that's going to be the easiest way to do it. So first, we want to remember the graph of y equals 3 to the x. It's going to have really similar structure to 2 to the x. Where it's going to essentially intersect at 0, 1, and it's going to go like this. However, our points are going to be 1, 3, right? 2 and 9, since 3 squared is 9, right? So if we want to graph with transformations, that means we are going to look into the x and realize we are going to move right 2 spaces. Oops. We look over here, it's a +4. That means we're going to go up 4. All right, so let's graph it. So let's pick on this point 0, 1. So we're going to go, all right, so instead of being 0, 1, which is here, we're going to go to the right 2, 1, 2. Then we're going to go up 4. So 1, 2, 3, 4. All right. So we know this is where my graph starts to decline. So this bit of the graph. And then we can also transform stuff like 1, 3. So we are at 1, 3, which is here. We want to go right 2 and then up 4, which is going to be here. And then lastly, I will move 2, 9, which was here, but we're going to go right 2 and up 4. So it's going to be my new point up there. So I've transformed all my points into being new points. And I can complete my curve. Since we moved up 4, where y is equal to 4 is going to behave like our new asymptote instead of y equals 0. And that's how you graph these using transformations. All right, let's keep going. The half-life of radium-226 is 1620 years. In a sample originally having 1 gram of radium-226, the amount A of T in grams of radium-226 present after T years is given by this function here, where T is the time in years after you start the experiment. How much radium will be present after 1620 years? So all you're going to do is plug in 1620 for T. So for number 1, we'll have A of 1620 is equal to 1/2 to the power of 1620 divided by 1620. This is equal to 1/2 to the 1, since 1620 divided by 1620 equals 1, which is equal to 1/2. And then for part 2, we are going to plug in 3240 for T. So that means we're going to have A of 3240 equals 1/2 to the 3240 divided by 1620, which is equal to 1/2 to the 2nd power, since this divided by this is 2. And this is equal to 1/4. Not too bad, right? Let's keep going. So logarithmic functions. Logarithmic functions are like kind of undoing an exponent. So you see y equals log base b of x is equivalent to b of y equals x. Now it's very important that all the bases are positive real numbers and that they're not equal to 1. So basically, I like to think of this as if you have some base, it has an exponent, and it's just equal to some number. A log kind of flips these around. So you have a log, your base goes down here, some number, and it will equal the exponent to which you need to raise the base to get this number. Example, 2 to the 3rd is equal to 8. This means that log base 2 of 8 is going to equal 3. So you see, what the log is asking you is, to which number do I raise 2 to get 8? And your answer is 3, since 2 to the third is 8. All right? Let's move on. So now we're going to switch back and forth. We're going to first write logs in exponent form and then write exponents in log form. So remember, the base is down here. That's 2. Exponents out here. That's 4 equals 16. Not too bad, right? Again, base is 10. Exponent is -2 equals this number here, 1 over 100. Lastly, our base is 7. Exponent is 0, and it's equal to 1. And that's really all you have to do. Let's try and go the other way. So we'll have log. Our base here is 3. Our number is 81, and it's equal to the exponent, because the exponent is 4. All right, number 2, log. Base 10. The number we're trying to get to is 1 million, and it's equal to the exponent, which is 6. Last one, log base of fifth of 5 is equal to -1, because that's the exponent. Not too bad, right? Let's keep going. The equivalence property of exponents is basically just a fancy way of saying b of x equals b of y implies x equals y. Essentially, what you're saying is if you have 2 to the 3 equals 2 to the x, then x must equal 3, because there's no other way, or there's no other power we can raise 2 to in order to get 8, or 2 to the third. Similarly, if you have 3 to the 5th equals 3 to the y, that means 5 equals y. All right? I can do more. 5 to the 7th equals 5 to the z. What does that mean z equals? Must be 7. They can get a little more complicated. So if you have, for example, 4 to the x minus 1 equals 4 to the 6. That means that x minus 1 must equal 6, which means x equals 7. Not too bad though, right? Once you have the bases the same, you can just look at these exponents. All right, let's keep moving on. So these are some more properties of logarithms. They are important to remember. The first one is just anything to the 0 power is 1. So whenever you have a 1 inside the log, you're going to get 0. And then you have b to the 1 equals b. So whenever you have the same number as the base and as the number inside the log, it's going to be 1. Stuff like that. So let's just kind of jump into the examples. Log base 3 of 3 to the 10th. So I want to know which power do I raise 3 to in order to get 3 to the 10. What exponent do I need? It sounds like a trick question. It is just the exponent that is sitting there. It's going to be 10. Next, we're going to look at the natural log of e squared. Now, the natural log is base e, if you didn't know that. The natural log is base e always. So ln of e squared is just asking you which power do you raise e to get e squared, which is just 2, right? Log base 11 of 11, that's our property number 2. If we have the same number in the base as inside the log, we're just going to get 1, since 11 to the 1 equals 11, right? And then lastly, oh, my code got a little messed up, but log base root 7 of 1. If we look up here at property number 1, anytime we have a 1 inside the log, we're going to get 0. So even though we have this ugly square root, it's just going to be 0. Not so bad, right? Next, we want to graph these functions. So I'm going to first do the log base 2 of x. So again, we'll have our table of x's and y's. And then we can't pick negative numbers because there's no way you can ever have an x in the exponent where 2 to the x will equal negative 1, right? Since 2 to the negative 1 is a half, 2 to the negative 2 is a fourth, and etc., we'll never get a negative number or really anything below 0. So we only worry about positive numbers. So I'm going to plug in 1, 2, 4, and 8, since those are powers of 2. So log base 2 of 1 is actually one of our log properties we just talked about. Whenever we have a 1 right here, it's going to be 0. Log base 2 of 2 is another one of our properties we just talked about. Whenever it's the same number as the base as inside the log, it's always equal to 1. Log base 2 of 4 is equal to 2, since 2 squared is 4. Because remember, we're looking for the exponent, right? And then log base 2 of 8 is going to be 3, since 2 to the 3 equals 8. All right, now I'm going to graph that. So we'll have 1 comma 0, which is here. Then we have 2 comma 1, 4, 2. Oops. 4, 2, and then 8 up 3. Now I am missing something. Because what happens if I plug in x is equal to, let's say, a half? Log base 2 of a half is equal to negative 1, since 2 to the negative 1 is equal to a half, right? We kind of just talked about that. So as I get closer to 0, I'm going to go down forever, right? So this is my graph of y equals log base 2 of x. All right, let's do number 2. So again, we'll need x's, we'll need y's. So let's see, let's pick for a half. We'll probably want to pick 1, a half, let's do a fourth, and 2. So remember, anything that has 1 inside the log is always 0. Log base a half of a half is equal to 1. Log base a half of a fourth is going to be 2, since 1/2 squared is 1/4. And log base a half of 2 is going to be negative 1, since 1/2 to the negative 1 equals 2. Because remember, negative exponents just flip your fraction. All right. So I'm going to have really small numbers. So what I'm going to do is only 2 tick marks every way. So I'll start with 1 comma 0, which is over here. And then when x is a half, y is 1. When x is a fourth, y is 2. And then when x is 2, y is negative 1. So we'll have something that looks like this. So it's as if you flipped your graph over the x-axis. Do you see? So instead of it being going forever down, it's now going forever up. All right, let's keep moving on. Domain. we did just talk about how we can never have 0 in here, right? Or negatives. So for number 1, all we're gonna do is set what's inside the log bigger than 0. So we'll have 2x plus 4 must be bigger than 0. That means 2x must be bigger than -4, which means x must be bigger than, let's see, -4 divided by 2 is 2. I'm sorry, -2. And we want to write it in interval notation. That means we do not want to include -2 because that's what makes our function equal to 0. I'm sorry, that's what makes inside the log equal to 0. We can't have that. But we can have anything larger than -2. For number 2, same concept. Anything inside of the natural log still must be bigger than 0. So we have 5 minus x is greater than 0. If you add x, that means x has to be less than 5. Strictly less than. You can rewrite it this way too if you prefer looking at it that way, but you're saying the same thing. So this is just saying that we can have anything from -infinity all the way up to 5, but not including 5. All right? And lastly, number 3, we'll have x squared minus 9 has to be bigger than 0. So this one's where it's going to get tricky. That means x minus 3 times x plus 3 has to be bigger than 0. All right. So let's figure out where x minus 3 is bigger than 0 and where x plus 3 is bigger than 0. So this means x is bigger than 3, and this means x is bigger than -3. And since 3 is larger than -3, we want the interval from 3 to infinity. Because if we take the interval from -3 to infinity, that means we'll include numbers that make this piece be smaller than 0, and we can't have that. So when it's greater than, we always pick the larger number to put in our interval. The next thing we want to do is figure out if there's any spot where they're both less than 0, since a negative times a negative is going to give us a positive. So we want to see if there's anywhere x minus 3 is less than 0 and x plus 3 is less than 0 at the same time. So this is going to be x is less than 3. So this is going to be x is less than 3, and this is going to be x is less than -3. And similarly, when we were greater than, we chose the larger number. When we're less than, we're going to choose the smaller number. So this is going to be -infinity to -3. Now we're allowed to choose from either of our intervals because either way, we're going to have a negative times a negative in this case, which gives us a positive. And in this one, we'll have a positive times a positive, which is a positive. So that means our answer for the domain is actually going to be -infinity to -3 union 3 to infinity. All right, let's move on. So these are some properties of logarithms that you'll need to use in order to separate your log. Some examples, like if we wanted to use the product property, we could have log base 2 of x times y equals log 2x plus log 2y. These ones you should these ones you should remember from an earlier table, but these ones are going to be the new ones. If you had, for example, log base 3 of 6 plus log base 3 of 2, this would be log base 3 of 6 times 2, which is equal to log base 3 of 12. So you see you can go either way, right? We can separate from multiplication into addition, or we can go from addition into multiplication. And you can do the same thing with quotient and power property as well. Power property, I like to think of, you can just take the exponent and boop it out front. See, now there's that exponent. So if you had log of x squared, that's the same thing as 2 log x. You just put him right in front. All right, let's go through some examples. So what we want to do is deconstruct this log to make it in the form of our properties. So the first thing we'll do is see that divides means subtracts. Okay, multiply is add, divides is subtracts. So that means we'll have log base 2 of z cubed minus log base 2 of x y to the 5th. This is equal to, see this 3 up here, we can boop him out front. So we'll have 3 log base 2 of z minus parentheses, since this is multiplication, log base 2 of x plus log base 2 of y to the 5th. So multiplication means I can split with addition. So this is going to equal 3 log base 2 of z minus log base 2 of x minus log base 2 of y to the 5th. And the very last step is just bringing this 5 out front. So your final answer will be 3 log base 2 of z minus log base 2 of x minus 5 log base 2 of y. And that's how you break up a log. Now what we're going to do is try to bring a log back together. The first thing I'm going to do is kind of remember this step I took from here to here. I had two things multiplied together, and then they were in parentheses with this negative out front. So I'm going to do the same thing here. So I'm going to say this is the same thing as log base 2 of 560 minus parentheses log base 2 of 7 plus log base 2 of 5, which is equal to log base 2 of 560 minus log base 2 of, what do you think? Well, if we're going to use our addition to multiplication property, that means we can multiply these two together. And 7 times 5 is 35. So this is now going to be equal to log base 2 of 560 divided by 35. And then 560 divided by 35 is actually 16. So this is going to be equal to log base 2 of 16, which is just 4. All that work for just the number 4. But not too bad, right? Okay, let's do the multiplication ones next. So ln of 5xy, that's just going to equal ln of 5 plus ln of x plus ln of y. Pretty straightforward, right? Because they're all multiplication, that means you can split them all up into addition. Next, we're going to combine an addition back into a multiplication. The tricky part about this is we can do these pieces first, so that's just going to be log of 12c. However, we need to bring this 2 back up into the top before we can multiply in the d to the rest of the logs. So this is actually going to be plus log of d squared. And then that's going to be equal to log of 12cd squared, since adding gets you to multiplying inside the log. Not too bad, right? Let's keep moving on. Next is going to be the change of base formulas. Essentially, given any log, you can always change its base. So if you had something like, I'm going to box in this formula. So if you had something like log base 7 of 10, you could change that to be like log base 2 of 10 over log base 2 of 7. Because this would be your b, right? And this would be your x. You can also change them to ln. So like log base 6 of 14. You could say that's the same thing as the natural log of 14 divided by the natural log of 6. I could keep going for a while, so let's just do one more. Log base 8 of 9. You could say that's log base 10 of 9 divided by log base 10 of 8. The purpose of this is sometimes to make things easier to put in your calculator, because not all calculators you can do a change, or you can do any base. Some of them only let you do log base 10 or natural log. All right, let's move on. All right, now we're gonna solve some problems, some exponential problems. All right, so first, if we can, the goal would be to get something like b to the x equals b to the y. That way we can just say, okay, x equals y. So the very, very first thing I'm going to do with any of these problems is see if, for example, 81 is any power of 3, if 60 is any power of 7, stuff like that. So for number 1, I'll have 3 to the 2x minus 6 equals. Now I know that 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27, and 3 to the 4 is 81. So look, we got it. 81 is here. So that means this is equal to 3 to the 4th power. Now I can use this really great rule and have 2x minus 6 equals 4. Adding the 6, you'll get 2x equals 10. So that means x equals 5. Not too bad, right? And then for number 2, I have 7x equals 60. 60 is not a power of 7, since 7 squared is 49. And 49 times 7, that's not 60. So we're going to have to do something a little trickier here. So what you'll do is you'll take the log of both sides. So we'll have a log of 7 to the x equals log of 60. Next, we'll use those log properties to bring this x out front, since x is the exponent. So it's x log to the 7 equals log 60. Now we are just going to remember that the log of 7 is just a number. If you put log 7 in your calculator, you're just going to get some decimal. So we can divide by it. So we're going to divide by log 7. And now we have x equals log 60 over log 7, which is approximately 2.1041. Not too bad, right? And lastly, number 3. Number 3 is going to be a little more complicated because we have base 4 and base 5. What I'm going to do first is take the natural log of both sides. So I'll have ln of 4 to the 2x minus 7 equals ln of 5 to the 3x plus 1. You can always take the log of both sides of any equation. Similarly, you can always multiply both of the sides of an equation by 2. You can always add 1. Yeah. So again, using log properties, I can bring my exponent out front. So I'll have 2x minus 7 times ln 4 equals 3x plus 1 times ln 5. Next, you're going to distribute the ln into these parentheses. So you have 2x ln 4 minus 7 ln 4 equals 3x ln 5 plus ln 5. And lastly, what I'm going to do is get all the x's on one side and everything else on the other. So that means I'll have 2x ln 4 minus 3x ln 5 equals 7 ln 4 plus ln 5, right? So I just moved the 7 over here and the 3x term over there. Okay, the next step is a little trick. You are going to take the GCF of this boy here, which is x, right? So you'll have x times 2 ln 4, because I took an x out of here, and I'm going to take an x from here, minus 3 ln 5 is going to equal 7 ln 4 plus ln 5. So that means that x equals ln 4 plus ln 5 divided by 2 ln 4 minus 3 ln 5, which when you put into your calculator, you'll get approximately negative 5.5034, but generally we prefer this form because it's more accurate. We don't like to approximate in math. Yeah, that's it. So just remember when you have the two different bases with complicated exponents to take the ln of both sides and then get all of your x's on one side, factor out the x, and then you divide by what's left over, and that's it. Not too bad, right? A challenge problem. We love a challenge problem. So we've got e to the 2x plus 5e to the x minus 36 equals 0. So here is the trick. I'll give it to you right off the bat. You are going to say let u equal e to the x. The reason you're going to do this is because e to the 2x is the same thing as e to the x squared. So what we're going to have is e to the 2x is going to equal u squared plus 5u minus 36 equals 0. And wow, it's all of a sudden a really pleasant quadratic that we definitely know how to solve. So we're going to take negative 36 and we're going to try to figure out factors that add to positive 5. I think 9 and negative 4 will work. So then we'll have u minus 9 multiplied by, u plus 9 multiplied by u minus 4 equals 0. So that means u plus 9 equals 0, or u minus 4 equals 0, which means u equals negative 9, or u equals 4. But since u was e to the x, we're not done here. This means e to the x equals negative 9, or e to the x equals 4. Remember, we can never raise a positive number to an exponent and get a negative. So we reject this solution. We can never have a negative. So that means our only viable solution is going to be this bit. If I take ln of both sides, I can bring my x out. So I have x ln e equals ln 4, and then ln e is 1. So this is just x equals ln 4. The natural log of e is always 1, so this is going to be something really great for you to remember, okay? All right, let's move on. Log problems. All we've got are log problems. So we've got log base 2 of 3x minus 4 equals log base 2 of x plus 2. Now, what's really nice is these logs are the same base, right? So all this means is 3x minus 4 equals x plus 2. Because these logs are the same base, we can just take what's inside. All right? And now this is really pleasant for us to solve. We subtract x, we get 2x equals, adding 4, we get 6, which means x equals 3. Really nice problem, right? So you just need to understand that when you have the same base, you can just take what's inside and set that equal. Okay, this was number 1. Let's do the second one. So the first thing we're going to need to do here is realize that we need to combine these using our quotient subtraction thing from log properties. So when they're subtracted, we can divide them. So this is going to be ln of x minus 4 equals ln of x plus 6 divided by x, right? from the log properties table. So now we can ditch the ln's and we can say this means x minus 4 equals x plus 6 divided by x. Multiplying each side by x, I'm going to get x squared minus 4x equals x plus 6, which means x squared minus 5x minus 6 equals 0. And then we look for factors of negative 6 that add to negative 5. I think negative 6 and 1 would do it. So we have x minus 6, x plus 1 equals 0, which then means either, I come over here, x minus 6 equals 0 or x plus 1 equals 0. So x equals 6 or x equals negative 1. There's one more trick to these problems, and that's that we have to plug them back in. So if you look, for example, at x equals 6, I'll have 6 minus 4, which is 2. That's fine. 6 plus 6 is 12. That's fine. Natural log of 6, that's fine. But what happens when I plug in negative 1 is I'm going to then have the natural log of negative 1, which I can't have. So we reject negative 1 and we only keep 6. So you need to remember to always check your solutions. Always, always, always. Because we cannot have a negative inside that log. Okay, let's move on. So solve for a specified variable. So for the first part, we want to solve for x. So I have p equals 100 e to the kx minus 100. So first I'm going to add 100. So I have p plus 100 is equal to 100 e to the kx. Then I'm going to divide by this 100. So I have p plus 100 over 100 equals e to the kx. Next, I need to take the natural log of both sides. And remember, when I take the natural log, I can do the log property where you take the exponent and put it outside. So that means I'll have ln of p plus 100 over 100 is equal to kx times ln e, and ln e is our favorite number, 1. So I just need to divide each side by k. And I get x equals the natural log of p plus 100 divided by 100, all divided by k. So hopefully y'all didn't think that was too bad. Let's do the second part. We have L equals 8.8 plus 5.1 log of d, and we want to solve for d. So first I'm going to get the log all by itself. So I'm going to subtract this 8.8. So I have L minus 8.8 equals 5.1 log of d. Then I'll divide by 5.1 on each side. So I have L minus 8.8 divided by 5.1 equals log of d. Now you may be wondering, well, when we had an x up here in the exponent, we took the natural log to get rid of it. So when it's in an exponent, we can take the log. What about when it's in the log? It's a good question. So we can remember that a log is just base 10. A log without a number is always base 10. So if I raise each side to the 10, I have 10 to the L minus 8.8 over 5.1 is going to equal d. The reason is, I'm going to use a smaller example. If I have 2 to the log base 2 of 8, I'm claiming this is just equal to 8. It is one of your log properties, but I want to tell you why it's true really fast. This is because log base 2 of 8 is equal to 3. So that means 2 to the log base 2 of 8 is just equal to 2 to the 3, which is 8. So do you see, so since we have 10 to the log base 10 of d, I can just pull down this d. It is a defined log property for you in your log properties table if you wish to review it. For now, let's move on. Next, we're going to do some applications problems. All right, so suppose that $15,000 is invested at the end of 3 years. The value of the account is $19,356.92. Use the model A equals PE to the RT to determine the average rate of return R under continuous compounding. So first, we want to assign all of our letters. So our original investment is P. So we have P equals 15,000. End of 3 years means time is 3. And the value of the account was this A. So that's 19,356.92. So we want to figure out what was R. So I'll just plug into my formula. So that means, which is here. So that means I'll have 19,356.92 is equal to 15,000 times e to the r times 3, right? Because it's RT, but it's generally more common to write it as but generally we'll write it as 3R just to make our lives easier. So I need to solve for R. The first thing I'm going to do is divide by 15,000. The second thing I'm going to do is take the natural log of both sides. So I'll have ln of $19,356.92 divided by 15,000 equals ln of e to the 3r. Remember, we can pull this out front and ln e is equal to 1. So I am just going to have ln of 19,356.92 divided by 15,000 is equal to 3r. Last, I'm going to divide each side by 3. So I'm going to have r equals ln of $19,356.92 divided by 15,000, all divided by 3. This is the exact answer. However, we will approximate it. So when you put that into a calculator, you should get 0.085, which essentially means it was approximately 8.5% was your rate that you were investing with. Okay. All right, so we have carbon 14 has a half-life of 5730 years. Write a model of the form Q of T equals Q naught e to the negative KT to represent the amount Q of T of the carbon 14 remaining after T years if no additional carbon is ingested. Alrighty then. So we are given our formula. It be right here. We are given that it has a half-life of 5730 years. So the goal in these problems are actually to find K. Okay? Because if we find K, then we can have a distinctive formula for our carbon. Essentially, Q naught is, that always represents the initial. So if it were like X naught, that would be the initial X, or whatever. Y naught would be initial Y. Q naught is the initial value of the carbon. And then T is time. So we really just need to figure out what K is. That way we can plug in a Q naught and a T and just be able to use this formula whenever we want to. So let's think about it. We have Q of T is equal to Q naught e to the e to the negative kt. We also know that this is a half-life formula. Half-life. So that means half, 0.5 of my original substance will be left over. It should always equal half of my original after all of this time has elapsed. Then I can essentially divide each side by Q naught to get 0.5 equals e to the negative kt. Problem that we've been doing for this entire lecture. Fantastic. How do I get rid of exponents? We take a natural log, right? So I'll have ln of 0.5 is equal to ln of e to the negative kt, which then means that ln of 0.5 is equal to negative kt. And I'm solving for the negative k, don't forget. So I'm going to divide by the negative t. Essentially, I need to divide by a negative and I need to get rid of the t, so it's kind of two birds, one stone. So that means k equals ln of 0.5 divided by negative t. Now we were given a t, so we can continue to solve for k. So that means this is equal to ln of 0.5 divided by negative 5730, since that's the t we were given. So that means k is going to be approximately equal to 0.000121. Lastly, we essentially just rewrite our formula using this k, and that's going to be your solution. So you'll have q of t is q naught times e to the negative 0.000121 t. And that is a complicated problem, but now you have seen how to solve it. Thank y'all so much for tuning in to our 14th lecture of the semester. I hope y'all have a wonderful rest of the day.